In part 2 of Zeros of Polynomials, we're going to take a look at irrational numbers and solving quadratic equations and polynomial equations when we have irrational zeros. So let's take a look at these. So working with irrational numbers, sometimes when we have a square root symbol, they are actually rational numbers. We saw an example of this in Zeros of Polynomials Part 1 when we identified rational and irrational numbers. If the square root can be evaluated and you end up getting a rational response or an integer answer, then those are just rational numbers. Square root of 49 equals 7. The square root of 100 equals 10. Each of these are rational numbers. Irrational numbers can sometimes be simplified. So here's an example of an irrational number that can be simplified. We have the square root of 12. The square root of 12 can be broken up into the square root of 4 times the square root of 3. Because 4 times 3 is 12, we're just able to break down 12 into its factors. You want to try and find the largest perfect square factor that can go into a number. Now, I'm going to write a little list on the side here, on the left-hand side, of perfect squares. So we have a list of the perfect squares up to 100. And so what you're trying to find is you're trying to find the largest perfect square that will go into the number that you're evaluating the square root of. If you can find a large perfect square other than 1, then you can rewrite the number as the product of its factors. Then you can separate the square roots, and we know that the square root of 4 is equal to 2. So we would, in this example, what remains is square root of 4 times square root of 3. Well, the square root of 4 is equal to 2, so we would say it's fully simplified when you write square root of 12 as 2 square root of 3. So we're going to do each of the following problems here. We have simplify each of the following. The first one is square root of 75. The biggest perfect square that can go into 75 is 25. So we're going to rewrite 75 as square root of 25 times 3. So then we end up getting the square root of 25 times the square root of 3. And the square root of 25 is equal to 5. So fully simplified, the square root of 75 is equal to 5 square root of 3. Let's do 45. The largest square root, or the largest perfect square that goes into 45 is 9. So I can rewrite this as the square root of 9 times 5, which we can break apart, the square root of 9 times the square root of 5. And then we end up getting 3 square root of 5, or 3 root 5. You can also say it like that. And with 24, the largest number that can go into 24 that is a perfect square is 4. So I can rewrite this as square root of 4 times 6, which is square root of 4 times square root of 6, which is equal to 2 root 6. And then lastly, we have 147. 147 can actually be written as 49 times 3. So when I break this down, I get square root of 49 times the square root of 3. The square root of 49 is 7, so I get 7 root 3. So this is just some practice with simplifying square root expressions. Going to do a quick review of solving a quadratic equation. As you saw earlier, being able to solve a quadratic equation is super helpful once you've determined at least one of the zeros of the polynomial. If what remains is a quadratic equation, you can use the quadratic formula to solve it, or you can use factoring. So in this case, for the first example, we have x squared plus 5x minus 24. So I'm going to look at the factors of 24 because I want to find two numbers that multiply to negative 24 and add to positive 5. So I end up getting 1 and 24, 2 and 12, 3 and 8, and 4 and 6. So if I have a negative 3 and a positive 8, when I multiply them, I get negative 24. When I add them, I get a positive 5. So I can factor this. to be x minus 3 and x plus 8 equals 0. To find out when this left-hand side equals 0, we take each of the factors, because 0 times anything equals 0. So I take each of the factors and set them equal to 0. And then we solve, and we get x equals 3 as one 0, and then we get x equals negative 8 as the other 0. So this is how we solve quadratic equations. We could also use the quadratic formula, which is x equals negative b plus or minus square root b squared minus 4ac all over 2a. This is something I'm not a huge fan of saying things should be memorized, but the quadratic formula is one of those things where I actually think it's worth the time and worth the practice, especially if you're going on in higher level math to have that memorized. You're going to need to know it. So there, you can actually look it up. There's a song where it goes to Pop Goes the Weasel. You could look that up if you're trying to find a ways to memorize that. But you could also use the quadratic formula to solve this, where your a here is 1, your b here is 5, and your c here is negative 24. When you solve this, though, you'll get the same result. For b, when I'm solving this one, I'm going to actually solve it using opposites and balance like we did for solving for the zeros here, because there's no middle term. So I can add 36 to both sides, and we get 2y squared equals 36. I'm going to divide both sides by 2, and I get y squared equals 18. When I take the square root, remember that gives us a positive and a negative answer. So we end up getting y equals plus or minus square root of 18. But I can simplify that because I know that 18 can be rewritten as 9 times 2. So we get plus or minus the square root of 9 times the square root of 2, which equals plus or minus, I need more room, plus or minus 3 square root of 2. So that's where simplifying radicals that we saw before comes into play when solving for zeros of quadratic functions or for polynomials. Again, I'm going to plug the quadratic formula. Here it is listed again. We're going to use the quadratic formula. I'm only going to go over one of these. If you want to try the others and then email me to check your answers, that feel free to do so. But we're going to do A. So my A, B, and C are your coefficients for your x terms, x squared, x term, and your constant. So x equals negative b. So my b is equal to negative 3. I'll write these to the side. A is equal to 1, b is equal to negative 3, and c is equal to negative 7 here in this polynomial, in this quadratic. So when I'm using the quadratic formula, I actually want to say negative b. So I would be saying negative, negative 3. Negative, negative 3 is equal to positive 3. You could write out the negative, negative, but I feel like that gets a little bit more confusing. So if you have a negative b value and you're doing negative, negative b, then that's just positive. So 3 plus or minus the square root of negative 3 squared minus 4 times 1 times negative 7. Make sure that's a negative. All over 2 times 1. Here we have 3 plus or minus the square root of 9 minus negative 28 over 2. 9 minus negative 28 is the same thing as 9 plus 28, which gives us 37. So I have 3 plus or minus the square root of 37 over 2. And that is fully simplified because the radical here, 37, is prime. So I can't break it down into factors where I have a perfect square other than 1. And so this is fully simplified. That gives us 2 answers because we have the 3 plus square root of 37 divided by 2. And we also have 3 minus the square root of 37 plus 2. This is kind of a shortcut to show that because both answers, both zeros, both solutions are written in 1 with that plus or minus sign. I'm going to do one more. I said I was only going to do one, but I'm going to do one more. I'm going to do B. We have x equals, our A is 3, our B is 5, and our C is -6. So we end up having -5 plus or minus the square root of 5 squared minus 4 times 3 times -6 all over 2 times 3. So that gives us -5 plus or minus what's underneath the square root. That square root part of this is called the discriminant. I like to solve that and simplify that. So I get 25 minus 4 times 3 is 12 times -6 is -72 all over 2 times 3, which is equal to 6. So we're left with -5 plus or minus the square root, and that's what, 97 all over 6. 97 is prime, and so that gives us our 2 zeros. -5 plus the square root of 97 over 6, and -5 minus the square root of 97 over 6. And so this is how we use the quadratic function to find solutions to a quadratic function, which are also those zeros. Now we're going to see some of this come into play. We're going to look at this example, and we're told the function below has at least one rational zero. Use this fact to find all the zeros of the function. So my constant term is 2, so my possible numerators are plus or minus 1 and plus and minus 2. My leading coefficient is a 1, so my denominator possibilities are plus or minus 1. So all my possibilities for rational zeros are positive or -1 and positive or -2. So I'm going to check that with our polynomial by using division to find one of the zeros. So we're going to try 1 first. 1, -4, 3, 2. We're going to synthetic divide. 1 times 1 is 1. -4 plus 1 is -3. 1 times -3 is -3. 3 plus -3 equals 0. 1 times 0 is 0. 2 plus 0 is 2. The remainder is 2, so this is not a 0. We're going to do the same thing for -1. -1, 1, 4, -4, 3, 2. Again, bring down the first value. So -1 times 1 is -1. -4 plus -1 is -5. -1 times -5 equals +5. 3 plus 5 equals 8. -1 times -8, or sorry, -1 times +8 equals -8. And 2 plus -8 is -6. This is not a 0. So next we can try +2. 1, -4, 3, 2. 2 times 1 is 2. -4 plus 2 is -2. 2 times -2 is -4. 3 plus -4 is -1. 2 times -1 is -2. 2 plus -2 equals 0. So 2 is a 0. So x minus 2 is a factor, and we would multiply it by x squared minus 2x minus 1. To solve for the other zeros, we can take this quadratic, and we can use the quadratic formula. So we have x equals negative b plus or minus square root b squared minus 4ac all over 2a. Just a silly aside, my initials Anna-Castine AC helps me to remember that 4ac. It's a little thing, but I mean, if you have the initials AC, that might help. I don't know. Anyway, all right, so negative b, my b is negative 2, so negative 2 is just positive 2 plus or minus the square root of negative 2 squared minus 4 times my a, which is 1, and my c, which is negative 1, all over 2 times 1. So that's going to be 2 plus or minus the square root of 4 minus negative 4 all over 2, which equals, I'm running out of space, 2 plus or minus the square root of 8 over 2, which the square root of 8, as we saw before when we were simplifying radicals, that's equal to, if I would do the side work if I needed to, the square root of 8 equals square root of 4 times 2. The biggest perfect square that goes into 8 is 4, which is equal to square root of 4 times square root of 2, which is equal to 2 root 2. So I have 2 plus 2 root 2 all over 2, because both terms in the top have a factor or multiple factor, can factor out a 2 or be divided by 2. I can divide both 2 and 2 root 2 by 2, which will leave me with 1 plus or minus root 2. And so those are my other roots. So my 3 roots for this polynomial are 2, 1 plus the square root of 2, and 1 minus the square root of 2. And those are my 3 zeros. Now remember, the degree was 3. I have 3 zeros. 1 is a rational 0, which they told me. And then the other 2 were irrational zeros. Now we're going to get even more complicated. We're going to look for imaginary zeros. So imaginary numbers are considered completely different from real numbers. They are defined by taking the square root of a negative number. The number I represents an imaginary complex number, and it's equal to square root of negative 1. Because if you think about it, you can't take the square root of negative 1. Because the definition of the square root is what number, or the concept behind square root is what number times itself equals the thing in the square root. Well, 1 times 1 equals positive 1. And negative 1 times negative 1, when you multiply negative 1 times itself, that equals positive 1. So there's no way you can get negative 1 in the real number system by multiplying the same number times itself. Because a positive times a positive is positive, and negative times a negative is positive. And so therefore, I can never get a number times itself and end up getting negative 1. So that's how they figured out that these imaginary numbers exist. And so when you have something like the square root of negative 9, we can write that or think of this as the square root of 9 times the square root of negative 1. Okay, and so then the square root of 9 is 3, and the square root of negative 1 is defined as being equal to I, so we can write that square root as 3i. So when we do that for each of these, we're going to get 2i. Here, we're going to get 2i root 5. That's a pretty one, right? Because this would be the same thing as square root of 4 times square root of -1 times square root of 20. Or sorry, not 20. At that point, it would have been divided out to be 5. Because 4 times -1 times 5 equals -20. We end up getting 2i root 5. Okay? You want to be careful not to put your I after, because you don't want it to look like the I is underneath the square root sign. So I always put it before, like I did right here. This would be 8I. And this one right here is tricky. We'd have 2 plus or minus, well, 48 could be written as 4 times 12. Oh, we can actually get 16, right? Because 16 times 3. So that's going to be 16 times -1 times 3 over 2. So I have 2 plus or minus the square root of 16, which is 4. I, because the square root of -1 is I, root 3 over 2. 2 can go into both terms in the numerator, so I can divide it out. 2 divided by 2 is equal to 1, plus or minus 4 divided by 2 is 2I root 3. Okay, so this gets a little bit more complicated because now we're going to see things that have maybe one rational zero, and then maybe it then has imaginary zeros. When you have a polynomial that has an imaginary zero, that means that in those points where it twists and turns, it doesn't cross over the x-axis again. So anytime you have that kind of situation, it's like when you have a quadratic that looks like this and never crosses the x-axis. That would have imaginary roots because it never, like there's no real number value on the x-axis that that function intersects with. And so it would have imaginary roots. So it's a kind of complex idea, but we can find these imaginary roots. So let's look at an example. It tells us that the function below has at least one rational zero. Use this fact to find all zeros of the function. It's written in descending order, so the order of our polynomial is fine. Our ending coefficient is 20, so possible values in the numerator are plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, and plus or minus 20. There's a lot. Our leading coefficient, though, is a 1, and so the possibilities for the denominator are just plus or minus 1. So it's essentially all of these values over plus or minus 1, which is just those values. So all of our possible values are going to be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, plus or minus 20. Now they tell us that the function below has at least one rational zero, so one of these values will have to be a 0 based on the rational zero theorem. So we could start with 1. So let's see what happens. 1. Write my coefficients of my polynomial. 1, -4, -2, 20. 1 times 1 is 1, -4 plus 1 is -3. 1 times -3 is -3. 2 plus -3 equals -5. 1 times -5 equals -5. 20 plus -5 is positive 15, and that is not 0. So the remainder is not 0, so therefore that is not a 0. All right, let's try. I'm going to try -1, but I have a feeling -1's not going to work either because we're not going to get a value large enough to get to -20. So I'm actually going to kind of skip around. Let's try 4. Sometimes you get a sense for what's going to work and what's not going to work. 4 times 1 is 4. -4 plus 4 is 0. 4 times 0 is 0. -2 plus 0 is -2. 4 times -2 is -8. That gives me a remainder of 12. So that didn't work. Let's try 5. These take up a lot of room. Give yourself a lot of space. Write it down on paper. We can't do this in our heads, so please make sure you're writing it down. We have 5 times 1 is 5. Negative 4 plus 5 equals 1. 5 times 1 is 5. Negative 2 plus 5 equals 3. 5 times 3 is 15, which gives us 35. That didn't work. Let's try it when we have a negative. All right, negative 5. Watch it be negative 1. That would make me so mad. It'll be fine though. Okay, 1, negative 4, negative 2, 20. We have negative 5 times 1 is negative 5. 4 plus negative 5 is negative 9. Oh, this is going to be way too big. Negative 5 times negative 9 is positive 45. Negative 2 plus 45 is equal to 43. That's not going to work. Okay, I could keep going with that one. Let's try negative 2. And then let's try negative 4. And then let's try negative 1 and watch negative 1 be the 1. Okay, so we have 1 times negative 2 is negative 2. 4 plus negative 4 plus negative 2 is negative 6. Negative 2 times negative 6 equals positive 12. Negative 2 plus 12 equals 10. Negative 2 times 10 equals negative 20. Oh my goodness, thank goodness we found one. Okay, so negative 2 is a 0. Okay, so if negative 2 is a 0, I'm going to erase this work over here. And I'm going to erase this work up here. We already found out that those were not zeros. So what I'm going to do is, if negative 2 is a 0, then x minus c is the same thing as having x minus negative 2, which is the same thing as having x plus 2. So that is one of our factors, okay? So then the remaining polynomial comes from the coefficients from that synthetic division. So it'd be x squared minus 6x plus 10. It doesn't factor easily, and so what I'm going to do is, since I already know my 0 from this factor, I'm going to use the quadratic formula on this to get my remaining 0. So I get x equals negative b, which is negative negative 6, so 6 plus or minus the square root of b squared, so negative 6 squared, minus 4 times my a, which is 1, times my c, which is 10. And you see how quickly you can do this if you have it memorized? It's super helpful. All over 2 times 1. That equals 6 plus or minus the square root of 36 minus 40. Oh, you see where we're going to get a negative number? Where we're going to get our I? All over 2. So then we get 6 plus or minus the square root of negative 4 over 2. Well, that's equal to 6 plus or minus 2I over 2. 2 can go both into the 6 and the 2. So I'm going to divide those out, and that leaves us with 3 plus or minus I. So those are our factors. We have 3 factors, or 3 zeros. Our 3 zeros are negative 2, 3 plus I, and 3 minus I. So this is an indication that we have a real 0, a rational 0, that actually crosses the x-axis at negative 2. But then the rest of the polynomial will have the twists and turns above the x-axis or below the x-axis and won't actually hit the x-axis again. I'm going to do this next section in a part 3. It'll be really short. Please make sure you watch that video and email me if you have any questions. Thank you.